Mars is a planetary graveyard, a silent, frozen world wrapped in a blanket of rust. It is a terrestrial world, but it is a fraction of Earth's size. Mars possesses only about half our planet's diameter, a physical scale that leaves it with just 38% of our surface gravity. The famous red planet color comes from the iron-rich minerals in the regolith. Over billions of years, these minerals have chemically rusted, creating a fine, oxidized dust that is lofted into the atmosphere by surface winds. Despite sharing a common origin with Earth, this smaller physical scale dictated a tragic evolutionary path. Between 4.1 and 3.7 billion years ago, during the Noachian epoch, this frozen desert supported a robust hydrological cycle. The southern highlands are carved with massive dendritic valley networks, indicating liquid water flowed consistently for millions of years. To the north, ancient shorelines suggest a vast ocean once covered a third of the planet, containing water comparable to Earth's Arctic. Flooding was also sudden and violent. Catastrophic outflow channels, some hundreds of kilometers wide, show where pressurized subsurface aquifers or melting ground ice burst forth, scouring the bedrock. This leaves us with a central question. If Mars once held vast oceans and a thick atmosphere, what happened to that water and what caused the planet to die? Mars lost its habitability because its smaller mass caused it to bleed internal heat far faster than Earth. Early Mars was protected by a global magnetic field generated by a geodynamo in its core. However, the iron-sulfur core was so thermally conductive that heat escaped too quickly, which halted the thermal convection necessary to maintain that magnetic shield. Once that magnetosphere vanished, the atmosphere was exposed to the solar wind, a stream of charged particles moving at 1,000,000 miles per hour. These ions physically collided with atmospheric atoms in a process called sputtering, literally knocking Mars' atmosphere into deep space. Without the weight of a thick atmosphere, the surface pressure plummeted to less than 1% of Earth's. Liquid water became unstable, either freezing into the ground or sublimating directly into gas. The planet's internal engine died, allowing the sun to strip away its habitable environment and leave it a shell. The cooling core also brought an end to plate tectonics. Mars transitioned into a stagnant lid regime, where the planet's outer crust became a single, immobile shell. Because the crust no longer moved, volcanic hotspots remained stationary. Lava could accumulate in a single location for hundreds of millions of years, rather than being distributed across shifting plates. This process created Olympus Mons, a shield volcano standing nearly 3 times the height of Mount Everest, with a base the size of Arizona. The enormous weight of these growing volcanic regions put so much tension on the stationary crust that the surface literally ripped open. This created Valles Marineris, a canyon system that dwarfs the Grand Canyon in both depth and length. These monuments are the colossal scars of a planet freezing in its tracks. Today, Mars is a hyper-arid desert. Its atmosphere is dominated by carbon dioxide, and without a thick blanket of gas to hold heat, temperatures can swing from 20 degrees Celsius at noon to -70 at night. The climate is driven by a seasonal carbon cycle. During the winter, a third of the atmospheric CO2 freezes into dry ice at the poles. In the spring, that ice sublimates back into gas, creating massive pressure gradients. These pressure shifts generate global dust storms. They can last for months, shrouding the entire planet in fine-grained iron oxide and blocking out the sun. In 2018, one of these planetary-scale storms permanently disabled the Opportunity rover. After 14 years of exploration, the dust blocked the sun so completely that the rover's solar panels failed, and its final message indicated that the sky was dark. Modern Mars remains a meteorologically volatile environment that actively resists exploration. We have shifted from looking for macro-scale fossils to analyzing micro-scale chemical signatures hidden within ancient lakebeds. In Gale Crater, the Curiosity rover identified long-chain organic molecules like dicane, preserved in 3 billion-year-old mudstones. These hydrocarbons are hypothesized to be fragments of fatty acids, which are essential components of cell membranes on Earth. More recently, the Perseverance rover discovered leopard spots on a rock in Jezero Crater. These small, light-colored nodules contain iron phosphate and iron sulfide. On Earth, these specific mineral combinations are often formed through microbial redox reactions, where bacteria derive energy from chemical interactions involving organic matter. While the surface is currently sterile, the presence of these specific mineral and organic compounds proves the planet once possessed every ingredient necessary to spark the genesis of life. Future human missions will rely on in situ resource utilization, the ability to extract life-sustaining materials directly from the Martian environment. The MOXIE experiment on the Perseverance rover provided a successful proof of concept. Using solid oxide electrolysis, it split Martian carbon dioxide to produce breathable oxygen, demonstrating that we can synthesize fuel and air on site. However, the soil remains hazardous. High concentrations of perchlorates make the regolith toxic to humans, disrupting thyroid function. Any future colony will require advanced filtration and bioremediation to manage this chemical risk. Despite these challenges, colonization efforts are moving forward. SpaceX's Starship program and upcoming sample return missions from NASA, ESA, and the CNSA represent a coordinated effort to bridge the distance between our two worlds. Mars provides the physical evidence that planetary habitability is fragile. Stepping onto its surface is a way to learn how to ensure the long-term survival of our own world.